Now, I am pleased to introduce our presenters for today's training, Trent Lewis and Emily Lewis. Trent Lewis earned his Bachelor's of Science in Agricultural Economics in 2000 from Texas Tech University. After a few years of experience in other industries, Mr. Lewis began Pond Medics in 2004 with his wife, Emily Lewis, civil engineer and lead hydrologist for Pond Medics. Mr. Lewis is a senior consultant with Pond Medics, specializing in areas such as hydrographic surveys, dam spillway rehabilitations, stream and stormwater conveyance management, hybrid shoring solutions, multi-scale dredging, and wetland riparian surveys using fixed-wing and multi-rotor drones equipped with a payload or infrared sensors. Mr. Lewis has been the president of the Opportunity Conservation Trust the last 7 years. Additionally, Mr. Lewis serves as the Aquatic Plant Management Society Texas chapter president. Mr. Lewis also serves on the board of directors of the Society of Lake Management Professionals. Mr. Lewis is active and presenting often to groups such as Texas Floodplain Managers Association, Texas Rural Water Association, Texas Parks and Recreation Society, and the American Society of Civil Engineers. Trent resides in Grayson County, Texas, with his wife Emily and their 6 kids. When Trent is not busy at Pond Medics, he's enjoying spending time with his family, doing things like hunting, fishing, spotting clays, riding motorcycles, and traveling. Since 1999, Emily Lewis has been practicing civil engineering with a specialty in surface water hydraulics and hydrology. Graduating with a master's degree in civil engineering from Texas Tech University, she moved into the suburban land development industry with a specialty in designing and engineering surface stormwater systems to enhance surface water quality through the cities and the neighborhoods, as well as designing stormwater systems that would safely move water downstream and prevent flooding. Prior to founding Pond Medics Incorporated in 2004, Emily worked for national and regional civil engineering firms. During her time at those firms, Emily was responsible for modeling, designing, and engineering natural and urban surface water systems. Her accumulated experience in civil engineering, hydrographic survey, and limnology is a key component to the success we have in our unique engineered surface water solutions that they provide to the clients each day. Emily's favorite quote is, "Quality in a service is not what you put into, it's what the client gets out of it." With that, I'm gonna turn it over Trent and Emily for their presentation.
Very good, thank you, Andreas.
Thank you, Andreas.
Okay.
Good afternoon, everybody.
All right, let me pull some slides up and we'll get going. Thanks for the introduction and thanks for the opportunity to present. We've got a lot of slides to get through today, so without delay, we'll just jump right in. And I'd encourage you, if something comes up and you have a question, submit it on the Q&A or on the chat. We'd be happy to save some time at the end to go over those. Dredge Smart, it's a program that we've designed over the years to help consolidate the process of putting a design together with the permitting and the planning logistics all the way through to complete construction set, even project administration. Pond Medics is a design build civil firm, so we have a lot of contracting experience. We not only just design, but we actually do the work as well. With that experience, we're able to put together a program to help other firms and civil engineers and land surveyors understand and build a successful plan for their projects that involve dredging. There's a few reasons why we do it, so we'll get into that and discuss those. Our experience is coast to coast. Our team has a lot of practical on-the-ground experience, actually performing jobs like $30 million jobs all the way down to $30,000 jobs. And you can see right in the center of that map, we've got a big heat map right here in Dallas and really Texas in general. There's a lot of dredging work that is happening in Texas at the moment. Infrastructure is aging. Sediment accumulations are becoming visible. And so the request for help in dredging is at an all-time high. And as your firms get requests too, we want to talk about how we put together a team of these specialists in order to help you pull off these projects. So I said building a team is important, and it may be the most important part because the people really make these projects happen. Anybody from engineers to hydrologists, all the way through to biologists, geotech, you've got robotics experts involved, the contractors, and even down to project administration. And what we do in this Dredge Smart program is build this team. And that's really the key component of the program. And what I hope to convey to you guys today is understanding and being able to identify which key players you need on your team in order to pull off these successful dredging projects. So today's agenda, we're going to talk about these 7 components: identify, quantify, strategize, devise and design, which is better just said, that's the papering out part, accomplishing the project, monitoring the project, and maintaining the project. Okay, so in our normal format, when we're giving these talks in person, we like to throw out the question, what do you see in this picture? What do we need to identify? And really, you know, we get responses like, I see some sediment, I see water, I see maybe some planktonic algae because the picture is green. We get a variety of different responses, and occasionally we get the response of, I don't see anything. And that's really the truth of the matter. We don't see anything in this picture, and that's the reason why the hardest part of our job is convincing somebody of a problem they can't see. Sediment is underwater normally, with the exception of dry detention or maybe some conveyance channels where you can see the sedimentation visibly. In a wet pond or a reservoir situation, you can't. And so how do we identify sediment? How do we know its distribution throughout the reservoir? And then how do we classify it? All of these components are important. All these questions to answer are important because we have to convince the client that there is or there isn't a problem that needs to be addressed. But how do we get here? Well, there's 4 sources of sediment loading: internal, external, organic, and inorganic. Internal sediment loading are things like down cutting, scouring of the shoreline. Maybe it's wave action that's pulling the shoreline into the center of the pond. It could be organic in the sense that there's a growth and decay cycle within that pond or reservoir of aquatic plants. Maybe they're native, maybe they're exotic, but that growth and decay cycle contributes to the sedimentation of that lake. External sediment loading, it can be in your watershed. What's unique about our political boundaries today is they are not aligned with watersheds. In studying the Native Americans and the way that they devised their tribal boundaries were based on watershed lines. And it makes a lot of sense because a lot of the problems that we deal with today could be avoided if political boundaries were drawn with watershed boundaries. So external sediment loading is a unique challenge because a lot of times the watershed is not controlled by the owner of the pond or reservoir or detention area. So it's important to identify where the problem is coming from and what you can do to fix that. Sediment loading contributes to this problem. And as you can see in the pictures, You've got a BMP there on the left that is at capacity and even failing underneath it. It enters the curb and gutter, and it goes down a tributary and ends up in the reservoir. The problem that a lot of people have is once the BMP has failed, they can't quantify the extent of the failure. Because once it enters the curb and gutter, once it goes downstream, once it enters the reservoir, now you have this, this problem of not being able to quantify the damage ensued by the failed BMP. So I wanted to also present today some ways that you can start to quantify those BMP failures and maybe start a case or a justification of how those BMPs affect the downstream assets. Okay, so data is critical. There are a few parts and components of this program that if you don't get it right, then the rest of the dominoes fall. Data is probably that's in the top 3 of those. So I want to explain, and in the next few slides, I have some drawings of what our plant sets look like. Oh, no, first, before I get there, this is survey. This is from hundreds of years ago. What's happened is boats would set sail and they would map big areas of water. They'd set out what's called a drag line. And in that drag line, they would have an anchored bottom with buoys on the top. And sometimes these ships would be 10 kilometers apart. And you'd have geographers on the ship. You would have navigators on the ship. They would triangulate. And as that drag line caught a high spot in the water body, you could see the effect of that in the buoys. And they would measure, they would map and triangulate all that. Well, today it's a little more scientific. We actually have stick figures. So in a lot of my talks, I typically have a whiteboard and I'm drawing some things. In lieu of the whiteboard, I just took some time to draw some stick figures so that you guys could see what I would normally draw in a presentation. But I want to talk about data and data collection, and we could spend the next 4 hours just on this because it is so important and because there are so many different components to it. But what you have in this illustration is 2 guys in a boat, and they've got their RTK GPS on a rod or on the boat, and the guy in the front of the boat on the left has the traditional kind of land surveyor methodology of taking a rod with a small, like 6 or 8 centimeter foot at the bottom, and he is trying to measure the depth in which he finds sediment. The guy in the back of the boat, or on the right, he's got his RTK GPS, and it's paired up with a survey grade sonar that is capturing the sediment, the top of sediment, and collecting that as the boat moves across the water. And in the lower right-hand corner, you can see that I've got 2 different illustrations of sonar. The one on the left is recreational sonar. That's your typical fish finder that you go pick up from the store. It's generally a 30 or 40 degree cone. And as you can see, it picks up a large part of the bottom, and the algorithms within that computer average the undulations in the bottom. On the right-hand side of the illustration, in the bottom right-hand corner of the slide, you see a survey grade sonar. A survey grade sonar, it can be multi-frequency, but generally it's going to have a very narrow cone, anywhere from 2 to 4 degrees. So your backscatter and your echogram is very precise in the area that's underneath the boat, and it's not averaged. That's going to come, we'll reference that again here in a minute, but I want you to keep that in the back of your head, because as we look at the data, we're going to see what these 2 methodologies, both the guy on the left in the front of the boat has with the rod, and then the guy on the back of the boat on the right, what he's doing with the sonar. So another really high-tech drawing that I came up with is what this looks like on the rod measurement, and as it relates to bathymetric data. Right? I'm not talking about sediment data yet. I'm just talking about bathymetric data. And bathymetry meaning what's the distance between the blue line and the red line in these illustrations. That's your water depth. That's what we're calling bathymetry. Underneath the red line and between the red line and the gray line is unconsolidated sediment. Unconsolidated sediment moves with laminar flows of the reservoir. It moves very much like water. It's very hard to detect manually, and we really have to have calibrated instruments to be able to find that layer of sediment.
It contributes a lot to our sediment.
Say it again.
It contributes, that unconsolidated sediment contributes a lot to our sediment whenever we're dredging a pond.
Correct, yeah. So then the next layer of sediment, which is between the gray and the black line, is consolidated. It doesn't move with laminar flows. It is more compact, but it does contain quite a bit of volume of moisture, anywhere from 40 to 60% moisture. The firm sediment is what you hear typically called the hard pan bottom or the native grade. And we consider these layers of sediment in a lot of the steps in the dredging process. But going back to how do we measure the top of sediment, right? This is really important for us. How do we measure the water depth or the bathymetry? Well, with the normal rod survey, what's gonna happen is this foot is gonna start to sink into that unconsolidated layer. And in the middle illustration, you can see that it's already past that top of sediment, and because it's so soft and so hydrated, it's starting to come up over the top of the foot. And the guy at the top of the rod in the boat is looking for resistance. He's looking to feel resistance on his rod to know, okay, my foot is sitting at the top of that sediment, or the Z value that we're looking for. By the time he's actually found it, he's all the way through the unconsolidated layer, and he's at the top of the consolidated layer. And especially in Texas, where we have a lot of organics, where we have a lot of fines that settle in the bottom of a reservoir, a manual rod survey to find the bathymetry is going to give you inaccurate data. So another component of this is not only the Z value, but it's also the density of points. So on the left, the guy in the front of the boat, he's probably running cross sections. And on each of those thin blue lines, he's got 5 to 10 data points that he's collecting. And you guys have seen plenty of cross sections across a creek or a pond or reservoir. He's collecting those. On the right, our methodology as far as hydrographic best practices is to do train set grids. We do them both east-west and north-south. And our point cloud is more dense. It provides us a higher resolution. And instead of collecting a fewer number of data points on the left, we collect 10 or hundreds of times more data points on the right. And I want to illustrate all these methodologies because this will come into play when we look at this next case study. So remember these two guys. The guy on the left is kind of your typical, hey, we're going to go figure this out and find the top of sediment. The guy on the right, he does it every day. He's a hydrographer. He knows the best practices and knows how to identify this stuff. So back to our data is critical. We have two illustrations here, both the same pond. The one on the left is the guy in the front of the boat. He's using his manual points. The one on the right is the guy on the back of the boat using sonar. This is a 3D bathymetry representation of the water depth. I want to zoom into the legends here on these maps. Again, the one on the left is no sonar, and you'll notice here that the points collected is 74 points. The one on the right, the points collected is almost 5,000 data points. And again, it goes back to our cross sections versus our train set grid and density of the point cloud. Well, in just the bathymetry, the difference between the two is almost 400,000 gallons of reduced capacity with the sonar. And if I may, let me go back to this. The reason is because there's a whole layer of sediment, of unconsolidated sediment, that the manual point survey did not pick up. And so it's estimating that the volume of water in the pond is greater than it actually is, because the sonar is bouncing off the top of the red line, whereas the manual survey is really down into the bottom of the unconsolidated layer. So it manifests itself in this way of falsely representing an increased capacity that's really not there. So when we quantify that, the misrepresented and inaccurate bathymetry, it manifests itself in inaccurate sediment volumes. So same pond, same sediment data. In other words, the data points that are on the left, those are the ground truthing points of the estimated soft sediment. Soft sediment meaning unconsolidated and consolidated sediment. So the sediment data on both of these maps is the same. The only thing that's changed is the delta analysis for the bathymetry. And you can see that on the left-hand side, there is 1,400 cubic yards measured. On the right-hand side, there's 3,300 cubic yards. That's almost a 2,000 cubic yard discrepancy on a 1.4 surface acre pond. So logistically, think about this. You've gone through this iteration, you've developed the plans, you've sent them out to your client and said, we have 1,400 cubic yards. The dredging contractor gets in there and finds out that there's a whole layer of unconsolidated sediment that has not been accounted for, and they start pulling it out and they're achieving the proposed contours. And now all of a sudden they're saying, we're double what was estimated. Now you've left your client in a situation where they may have to pay the contractor more. They're going to be scrambling, and this is not a situation you want to be in. So data is so critical to these projects that it's what lands most engineering firms in the court, having experts like us up on a stand saying, let's see the data and let's figure out how this came to be. And we work with a lot of engineering firms, and the thing that we find most is that we can trace all the problems of the project back to this single step of how the data was collected. Emily, would you agree with that?
Yes, absolutely.
So what helps in determining sediment volume is if you have record or as-built drawings, what we can do is we can take the subjectivity out of the ground truthing of the sediment depth, and we can know exactly what the design contour is. And then we can take our bathymetric representation and do a delta analysis and come up with the difference between design contours and grading within that wet pond or reservoir and what's actually there. So this is an example of an independent school district that built a new middle school. The first thing to be built was the wet pond. They used it as borrow-fill for benching their site, but they also used it just to collect stormwater and detain as they were developing. 18 months later, the school is built. The contractor is asking to close out the project, and somebody said, hey, wait a second, we've had a lot of flooding, we've had a lot of rain, we've had a lot of BMPs fail because we pulled up the report and found that silt fence and straw wattle weren't maintained. And somebody had enough forethought to say, hey, we think that a lot of the sediment has ended up in our wet pond. So they called us, they said, hey, could you do a survey, and then we'll send you digitized design contours, and you compare what the difference is. Well, the difference in this project was 4,000 cubic yards of fill that was not supposed to be there. So they presented it to the contractor drained the pond, they ended up removing the 4,000 cubic yards, and essentially the school district kept from being the benefactor of a $500,000 dredging project right off the bat. So it was very beneficial to have the design contours with our survey grade bathymetry to measure this. All right, so the strategizing, if you remember our outline of 7 things, we've identified where the sediment is within that reservoir. We've quantified how much there is in the distribution model. And now we're going to strategize. We have this data, and now we have to figure out how are we going to use this data to accomplish our client's goals. The example on the right is a project that we did in East Texas for a property owners association that had multiple string of lakes. They called us, they said, look, we've got a problem with our lake. There's a ton of sediment. We need to have a study to have it removed. So we did all the data calculation, all the data retrieval and then processing. And we sat down with them with the surveys, and we said, okay, here's the things that we need to look at. The bathymetry versus sediment. So in the middle of that lake, you've got 17 or 18 feet of water, and you may have 6 or 8 feet of sediment, but does 6 or 8 feet of sediment in 17 feet of water affect your goals? Your goals being recreation and fishing. Well, the answer was no. We had plenty of water out there. So we said, okay, if that's the case, then we really need to just surgically look at the shoreline of the lake and figure out what needs to be removed around the shoreline. But before we got to that point, they started really fixating on the sediment that was in the middle of the lake. And we had to go back to this point number 3 on this list of accomplishing goals and say, look, we're not after that sediment, right? Your goal is you want to be able to get boats out of the boat dock when the lake level drops a foot or 2. So we went back to their goals, reoriented ourselves, and then took this surgical approach of looking at just the shoreline. Well, in the distribution model of soft sediment that was hydraulically dredgeable, we found out that there was not much there that was hydraulically dredgeable. So that necessitated the means of excavation and excavation around boat docks. Well, as we work down our list of strategizing, we get to unintended consequences. The unintended consequence of excavating around those boat docks is twofold. Number one, we could have a geotechnical situation to where there's rock or shale or sand that as soon as we start digging around the boat docks, we're just creating a drain hole in the bathtub. So that's not a good consequence to our action. The second thing is we start digging around boat docks. Some of them have been there since the early 70s. The pilings are not very deep, and we start to lose structural integrity of the boat dock. So we walked through the unintended consequences and said, wait a second, if we're building a team to pull this off, now we're going to need to bring in the geotech, and now we're going to bring in a structural engineer to assess the unintended consequences of our actions. The next thing, once we get that figured out, we said, okay, you have an entry fee, right? We've got the planning and engineering and design. We've got the surveys. We have the permitting. We have all of these things to get done before we even start moving mud from point A to point B. Once we get to moving mud, how much of your budget is taken up by just the entry fee of planning, permitting, design, and engineering? Well, in this iteration, they said it's over 50% of our budget. So our recommendation to them was, okay, keep socking money away in the coffers. Let's save up to where your entry into the project for planning, permitting, design, and engineering is 25 to 30% of the project, so you can spend 70 or 75% of your budget on the actual moving of the mud, accomplishing the goal. And then the logistics and permitting, right? Moving mud from point A to point B sounds easy, but it tends to be very difficult. And the permitting does play a part of that as well. Let's see, I'm gonna check over here to my Q&A since I don't have that pulled up. See if anybody's got questions yet. Or the chat window. Okay, nothing yet. I'm either doing a really good job of explaining it, or you're just completely in a cloud. All right. If you have them, go ahead and pop them up when you're ready.
The logistics part for this had a lot to do with being able to digitize the original bathymetry of the lake and being able to talk to the landowners around the lake that wanted to have their docks cleared, finding out that there really wasn't the amount of water available or the amount of shoreline available that they thought was available.
Yeah, that's a great point. We ended up digitizing 1968 record drawings of this lake, and in digitizing those and then comparing them with our 2019 bathymetric survey, we found out that there was less than a foot difference in the delta analysis. So you know, anecdotally, people were sitting at the table saying, 25 years ago, we didn't have this problem. But when we substantiated it with the data and came back to them and said, we don't find a considerable change, right? There's not 6 or 8 feet of additional sediment around your dock that wasn't there 20 or 30 years ago. It kind of disproved a lot of their anecdotal evidence, which was helpful in us in, again, convincing them of a problem they can't see, and also convincing them that there may be some unintended consequences that we need to consider before we just start moving machines out and digging holes.
Right. So it goes back to how important data is whenever you're trying to strategize.
Absolutely. Okay, so the next, and let me reiterate that this strategize, this is the heavy lifting of the project. This takes the most amount of time. This, you know, as we go through some of these bullet points, and this is not exhaustive, it's just representative of a lot of the things that we consider. But in going through a lot of these data points and considerations, as we change and modify one of these, then the 4 more have to modify.
Right. It's an iterative process, and you're constantly going back and forth.
Correct. So then once we get through that heavy lifting of strategizing and figuring out the logistics and having the conversations and making sure that the planning and design is going to meet the goal and the budget of the client at the end of the project, then we devise and design. This is the engineering portion. This is the papering out. This is the easiest part of the whole process, because once we've got all of the strategy, now we just need to paper it out and make it legible and make it easy to follow by a contractor that may be bidding on it, maybe conducting the work. But if your strategy is done correctly because your data was precise, then the papering out is easy, and the papering out means that when it goes out to bid, you get very competitive, comparable bids. If you have bids that come back that are way off base, you've got a really high, a really low, a couple in the middle, that's probably representative of the plans were not specified in a way that everybody understood the project the same. Okay, so we talked about permitting. And in Texas, we deal with these main agencies. You may be looking at that slide going, man, Republic Services, I know they're not an agency. They're not an agency, but I put them on there, and they represent the special waste that sometimes comes out of wet ponds and reservoirs. If they're old, they haven't been dredged in a while, they've accumulated a lot of sediment. They may have contaminants like arsenic or lead or mercury, things that exceed TCEQ's thresholds for being safe, and they need to go to a Class 2 facility to be handled properly. So in the iterative process of going through which permits will be necessary and how do we maybe lighten the permitting load of a project, we always consider the waste and the spoils. Does it need to go to a certain place? And maybe if it's not going to a certain place, maybe there's something legally that we need to do if it's going to private land to protect the owner in the liability of that sediment later on down the road. So I want to talk about experience crossroads, because when we sit in on meetings with other firms and maybe we're sub to the prime, maybe we're coming in just to handle these components while the prime is handling other components. The things that come up most often that maybe make people squirm in their seat at that conference table is these main things: hydraulic versus mechanical. We're working on a project right now that I'll keep unanimous just to protect all the parties involved, but the engineer didn't have any help on the project. They specified in the technical specifications that they wanted the sediment removed hydraulically. So they were to get bids back from hydraulic contractors who could, and hydraulic meaning they can suck and pump out the slurry, dewater it out of the reservoir, and then haul that off. The problem was their performance measurables were in terms of mechanical dredging. So they had written the specs and requested hydraulic quotes, but they had designed it for mechanical. They designed it to achieve contours in that wet pond that were not possible with hydraulic dredging. And so, you know, at this time, we're in a situation where the specifications were so mixed up. The contractor is in a dispute right now for payment, and the client who hired the engineering company is after everybody because they're not winning on the project. So this is where a contractor with contracting experience, like the reason we're design build is because our contracting experience, we understand the difference between hydraulic, mechanical, and what's physically possible with those methodologies. It's very unlike any grading that you've ever done in civil engineering. It's unlike any tolerance within a margin of error that can be attained with mud versus maybe say grading a parking lot. So understanding the methodologies, the opportunities, the challenges, the pitfalls is super important with the methodology. Quantification. So another big question that ends up throwing across the table is, how do we quantify and how do we know precisely how many cubic yards are in a reservoir? The quick answer to that is it depends. But the main thing that needs to be understood is that quantification is an estimate, right? If you think back to that previous slide with the cross-section or the grid, we have a point cloud of data that we try and get as dense as we can, but in between those points, you have interpolation between points. And you want to try and reduce the interpolation between points, but there is an estimation that happens that the cubic yardage is not per cubic yard, which leads us to the next crossroads is in a dredging project, do you specify a lump sum payment for the project, or do you specify a per unit payment for the project? In our experience, the lump sum specification for payment is the best win-win, as long as there's a performance measurable that's included. What I mean by that is the performance measurable is not a quantity of cubic yards removed from a reservoir. The performance measurable is, did you get the right amount of cubic yardage from the right area of the reservoir to achieve the goal that we wanted to achieve? In saying that, there's a margin of error in that quantification, not only because the interpolation of data points, but also just because of the nature of the sediment. We talked about unconsolidated sediment that's very hydrated, that when we perform our shrinkage tests, we have to consider the difference in dewatering of each of those strata. And there may be all three strata represented in a dredging project in one single reservoir. So the margin of error has to be taken into consideration, and that's where per unit pricing really becomes the downfall of the project, because you end up paying the contractor ends up getting paid on an estimate, and then the client ends up paying on an estimate, which is not a win-win. It's always a win-lose. Somebody's going to lose out on that margin of error. The pre-dredge estimate. We get a lot of questions on this. How do you do this really well? When you have record or as-built drawings, we can take all the subjectivity out of it. But despite what instrument salespeople want to tell you that acoustically we can measure sediment depth, the reality is in our 10 or 15 years of experimenting with multi-frequency, dual beam sonars, we're not getting the data that is representative of the sediment in those reservoirs the way that it needs to be represented. So we can take subjectivity out of it by using record drawings or as-builts to determine our current sediment quantity. Or if not, then we have to use some ground truthing, and the ground truthing is an estimate. It's not exact. So when you look at a survey and it has the sediment distribution map and it says the estimated soft sediment quantity is 4,221 cubic yards, that is an estimate, and there is a margin of error there. Another thing that we end up seeing a lot too is survey aging. So we started on a project with the client. Client says, let's get going. We collect the data. We go through all of this, all the strategy, all the iterative process. Each iteration takes time. We end up papering it out. We've got a set of plans. We're ready to go out to bid with this. But the initial survey was done 18 months ago. We have to consider the survey aging, because if the 18-month-old data goes out and contractors look at it, the client is immediately put in a position of jeopardy, and maybe even sometimes legal retribution after the project is complete, because the contractor says your data was old. So our rule of thumb is, if the data is within 3 months of the project, it's good data. If it is older than that, then maybe we get to the end of the planning and papering it out, but we just need to go back. We need to do a quick bathymetric survey again. We need to input that data, the new fresh data, into the plan set, and then send it out to bid. The last and maybe most important part of this is data responsibility. Who is responsible for the data? In a lot of bid packets that we see, a lot of construction plans that we see that are done by engineers that don't have the full scope and picture of dredging, we see that data responsibility is given to contractors, and it's given outside of the responsibility of the client. And that's a very dangerous place to be, because as you saw in the previous slides, maybe the methodology of the data collection protocol is different than what the plan set was built on. And additionally, in the exchange of the dollar, if a contractor is paying a surveyor to do the data collection, maybe it's post-dredge survey, maybe it's a progress survey during the dredging project, there's a lot of soft numbers that can happen in that. So the main thing that is stressed on this particular slide is the client needs to maintain control of the data and maybe be the one responsible for the data even throughout the project.
Mm-hmm. Because data is so important in doing this project well, then the client's ability to manage and maintain that control over the project is paramount.
Real quick, I see a question from Andreas. Question is, if volume is paid per unit, do you measure wet or dry sediment? That's a great question, and one that gets mixed up often, and we end up being in the middle of it. But if we can get ahead of that and get it early, this is a great pitfall to avoid. If your measurement is done in situ, meaning in the reservoir itself during planning and design, then your measurement of progress or performance of the project has to be done in situ. You can't measure a dewatered stockpile as a performance measurable. You have to measure that in the same way that you plan the project. Great question there. So clearly you can't measure a dewatered volume during your planning, otherwise the project would be done. So you have to do it while it's wet, which means that you have to essentially do a delta analysis of bathymetry on the project in situ as well. All right, so the next—
For the post-dredge survey.
Yeah, for the post-dredge survey, thank you. The next step in this 7-step process is accomplished, right? This is, it's gone out to bid, we've gotten contracts back, we found the most valuable bidder, the most responsive bidder, and now they get out there and actually do the dredging work. We're working with mud, we're working with unseen objects, we're working with undulations and trash and debris, things that have accumulated, especially in an urban environment. So there are some things that come up during the accomplishment of a project, but with a good plan set, those are easily handled. We don't want to end up anything that says, look, you specified 3,000 cubic yards of removal in your plan set. However, we've found 10,000 cubic yards. That's the thing that we want to avoid. That's what makes accomplishing it really easy if the plan set is done really well. So I'm down to my last 2 or 3 slides. The next step is monitoring. We have both in progress and in project monitoring and post-project monitoring. In project is the progress and post-dredge surveys. You can see our drone boat there on the slide. We can do this autonomously. We can follow the same transects. We can monitor data collection through telemetry controls on the shoreline. It's very rapid data collection, and it's very rapid data processing for real-time decision making. So you definitely, on the larger projects, you want to do progress delta analysis to where we're seeing how much removal the contractor is doing. And then post-dredge, this is very important for payment verification. Yeah, and for volume that's being removed. It's important to the contractor, it's important to the client, it's important to the contractor because before they demobilize, they want to make sure that they've gotten everything that was specified so they can get paid. For the client, they want to have confidence that when they stroke the check, they're getting what they paid for. Because again, it's all underwater. Who's going to verify that? Where we take the subjectivity out of that data analysis is we're using that survey grade sonar instrument to find the top of sediment, the Z value. In the post-dredge or a progress survey, we're not using subjective rod measurements and ground truthing. We are using the delta of an instrument reading, which is very important. And in that instrument reading delta analysis, if there's a discrepancy in the data, we can go back to the backscatter or the echogram of that data and pull raw data to justify, yes, there is a problem, or no, this is a data problem. Maybe there's an anomaly within the data. If you have an instrument that's only outputting to a NEMA device a bottom number, like a bottom depth number, like a 3.3 meters or something like that, but you can't see the backscatter or echogram, that's a big problem. You have to be able to justify that instrument reading and the data it's outputting. So in post-project, after the project's done, we can do bathymetry only to track future sedimentation, because again, we're just doing the analysis of different data points in time. We can do it autonomously, which reduces cost, and we can make real-time decisions as well. Lastly, the maintenance, right? Nobody likes to go into a 6 or 7 figure dredging job when you can literally do smaller chunks more frequently if you have the data to know where that sediment is accumulating, maybe outside of a stormwater pipe that's coming into a wet pond. Just annual or semi-annual surveys will help track this. And the more data points we have in those surveys, then the better trajectory we can have on the planning. So there's a few things getting ahead of the curve on this. This is mainly dealing with municipal clients. O&M manuals for sedimentation survey, remediation monitoring. In other words, explaining this process to future owners, making sure that record drawings include hydrographic surveys. That, you know, if you pull up a set of as-builts, you don't want just a big white hole in the middle of that plan set with no contours of your wet pond or your reservoir. We want to see hydrographic surveys a part of those record drawings. Your stormwater BMPs include basin sedimentation monitoring and sediment recovery. Once that BMP has failed, how do you actually go back and quantify the extent of that failure so that you can take that back to the originator of the sediment and say, hey, there's some mitigation that needs to happen for restoration. Holding sedimentation symposiums. Most people don't know about this type of stuff. They just find out that there's a problem because maybe they've seen an increase in algal blooms. Maybe they've seen harmful algal blooms that are creating toxicity problems. Those are the symptoms to the problem of reduced capacity due to sediment volumes. But educating people on this is extremely important. And a guidance document. If you're designing and working with clients that involve surface water systems like this, have a guidance document for them so that when you make the handoff, the project is complete, you're able to tell them, look, it's not done, right? There's maintenance that's required for that. There's 3 components of maintenance. It's biological. You're gonna have fish that end up in that lake. You're gonna end up with plants in that lake. You're gonna have chemical, right? The water chemistry is going to change. You're going to have physical attributes of that lake, all of which need a level of maintenance and management by a trained professional. Giving them that guidance document for their surface water assets is extremely important. And then there are some progressive things like cities can adopt some water quality enhancement ordinances, so on and so forth. So we have about 7 minutes left. That's the end of my slides. Bob has a question. If you've got questions, feel free to input them. We'll address them in the next 6 or 7 minutes. Bob says, how do you determine if there is contaminants in the sediment before a contract is awarded? That's a great question, Bob. We take both core samples and sediment samples. We send them to the lab. We do a set of constituent tests that basically spits back an analytical report that for each of these components. Now, the key in doing this is there's not a boilerplate test for sediments, because depending upon where that disposal goes, where the sediment disposal is happening, may determine. So let's just take class 2 landfills, for example. You've got waste management, you have Republic Services, you've got TCEQ has some disposal sites. Each of those sites have different contaminant requirements, because thresholds, exactly. Thank you, Emily. They have different thresholds because each of those sites is regulated under a different TCEQ permit. There's not a landfill that has a blanket TCEQ permit. Waste management may have one that requires a certain panel of tests run versus Republic Services, which is another set. So understanding maybe the closest landfill in proximity to the project or where that sediment needs to go will determine which analytical report and which constituents need to be analyzed for the sediment testing.
So it goes back to the iterative process and strategizing, because we can run a panel for the closest landfill and maybe we exceed a threshold for that closest landfill. Well, there's nothing we can do about that. So we're going to have to go back, find another landfill that threshold can be, that will accept that threshold that we have, or the amount that we have. And then we're going to have to reiterate the trucking costs and all of those things. So it goes back to the strategizing and iterative process of where it can go and how often that we have to retest the contaminants again, or go through another sample to get to the place that it needs to go to.
Absolutely. Another question from Bob. If you find contaminants, do you have to determine the source of them to see who pays for the treatment? No. Once it's come off the watershed into the wet pond or the reservoir, it is now the responsibility of that landowner that owns or manages the reservoir where that contaminant and sediment is contained. It's not necessarily the responsibility of upstream. Now, I'm not an attorney, and I can't tell you the legality of this, but what I've seen in our experience on different projects is if you know of activity that's happening upstream or is about to happen upstream, it is best to come in and go ahead and collect your samples, run your tests, do your bathymetric survey, even do your sub-bottom profile, which is your sediment distribution model. Go ahead and do all of that before your upstream neighbor begins construction or before they start modifying the watershed. If you can collect that data and then collect in-progress data of construction or modification of the upstream watershed, and then a post-construction data set, now you can start to build a narrative anecdotally backed up with the data to maybe talk about liability of those actions. Again, we're not attorneys. You need to consult your legal professional to do that, but we have worked on projects where we bring in that data to help the legal professionals build that case.
Again, because data can be your client's, data is your client's best friend. So.
Yes, absolutely. And that's why instruments are so important. That's why if you end up in a mediator's office or, God forbid, a testimony stand or a courtroom, that the data that you collect is satisfactorily backed up with the underlyings, like for sonar, it's the backscatter and it's the echogram. Those are the things that will justify positions in court. I think the last thing that I'll address in our few minutes, kind of sticking to Bob's theme on sediment, is the big question that comes about is who owns the sediment when it leaves the originator's site? So if you are the sediment generator, it's coming out of your pond, your client's pond, and it gets put in a truck and it gets hauled away. Let's just use the scenario that gets hauled away to a private landowner. The private landowner accepts it. Maybe you've run the panel of analytics on the contaminants just to give them a peace of mind. Everything checks out fine. But 10 years from now, you get a phone call, your client gets a phone call and says, hey, there's a problem with this sediment. I think you still own it. You do need to protect your client. You do need to get with your attorney and your legal counsel and write a release of liability for that sediment. Because there are situations where even though there's been like a time lapse that's gone on, everybody accepted it in the beginning, it was kind of a handshake deal, you need to protect your client and make sure that you've got a release of sediment so that there's not any liability hanging over their heads years down the road from the project. All right, it's 1 o'clock. So Andreas, do you want to maybe wrap things up?
Yeah, thank you, Trent and Emily. I really enjoyed the presentation. Well done. Thank you. Well, to everybody, thank you for participating in today's ASCE Texas section technical webinar, and thank you very much for our presenters, Trent and Emily. As mentioned before, individual registrants will receive an